All right, we are now recording. I think I'll go start with this one, but if I need to, I'll get to the other slide soon. Okay, now those who just got the test, and those who got it before, in case you didn't get this, I already marked you here, and I marked you here. Okay. Number 1 has one answer, you put it on that blank. Number 2, you'll notice, has 2 answers, so put A above the line and B below the line. 3, 4, 5, 6, 7, and all have one answer, put them on the line. Number 8 has 3 parts, so put A above the line and B and C below the line. You got plenty of room there for that. 9 has one answer, and then 10 again has 3 answers, put A above the line and B and C below the line. So pretty easy to see. All right, any questions? Either yes. Oh, you need one. All right. Oh, even swap. Okay. Number 7. Oh, in the circuit below. Look at that. I think that's the one in number 8. Yeah. I'll have to check the key to see if that is the one, but if it's not, I'll figure it out. Yeah. Wait. Yeah. See, the circuit below in number 8 is a 36-volt power source, okay, voltage source. So in number 7, it won't be, well, it won't necessarily be 36. You figure out what it would be. But you almost have to do number 8 first, because you have to find the current. No, they give you the current. You have to use those resistors, though. And notice those resistors are in series, okay. So should be a fairly straightforward problem to do. Okay.
So the circuit below will be the one in question.
I'm sorry?
It says in the circuit below, that's for question. Use the circuit for question A to answer number.
Yeah, refer to those 3 resistors in series. Yeah. Are you hoarse today? Oh, wow. Sorry. You don't sound like yourself. Okay, I think I marked everybody here. Let me do my little blurb that I'm going to do from now till the end, hopefully if I remember to. Please, folks, there are 2 people, two people who have not turned in test 1. Uno. Okay? 2 people who have not turned in test 1. Please get those in. I need to get these back to everybody. On test 2, 2 people who haven't turned in test 2. And not necessarily the same 2 people. Test 3. 1, 2, 3, 4, 5, 6 people haven't turned in test 3. Test 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 haven't turned in test 4. So please try to get those in, caught up over the weekend. Turn them in next week, because next week we meet Tuesday and Thursday evening, okay? And then Thursday I'll be giving you the test on chapter, it's actually going to be 18 and 19 together, because the test bank had very few decent questions on one of these 2 chapters. I think it was 18. So we're combining 18 and 19 for the last test. And I don't want you under the pressure of having to do 5 tests in one weekend if you don't turn in the others this weekend. So please, please get those tests to me next week. I want to get all those off my desk so I don't have to carry them around anymore. I'm too lazy for that. All right, any questions on anything we've covered so far? How we're going to go, what we're going to do. Okay. Now, we just got started on Chapter 18 last time, 18.1 on page 502, and we got down almost the middle of 18 on page 503. Sorry, I've got froggy voice. And we already said a lot of this, so let's just hit it again. Every magnet has two what? Two poles. You cannot have a magnet that they would call a monopole, single pole magnet. You can't. In fact, there's an old illustration. If you had a bar magnet, okay, and if you put it in a container that had iron filings, you'll see all the iron filings go up on the North Pole and South Pole, whichever they are, and they all congregate around there. Almost nothing touches the middle of the magnet. They don't stick. They just it's just empty. Okay. Now, if you were to break that magnet in two and then put iron filings on it, you'd find that middle of the magnet that didn't attract the thing before now attracts like crazy on both of the pieces. Because anytime you have a magnet, you have two poles. Magnets are dipolar. I started to say bipolar, but they're not. Okay, they're dipolar. Okay, all magnets are dipoles. Now, both poles of a magnet attract iron filings. So does that mean the poles are the same? What you think? Second? No, they may have the same attraction, but they're not the same, because if you took a known magnet and held it close to an unknown magnet, and let's say the unknown magnet's like this. If you pick a pole, north or south, I don't care. Pick one. Anybody? North or south? Second? Pick one.
North.
North. Okay. So you know this is the north of this magnet. Okay? And this one is sitting down here, say hanging on a thread. Okay? And you bring this one close. What might this pole do?
Attract to it.
It may attract to it. What would that tell you about this pole?
The strongest.
Second?
Well, no, the one in your left hand is a little stronger than this pulling.
Okay. Well, it doesn't matter which is stronger, but what can you tell me about this pole?
It's moving
It did move. Why?
because of the magnet.
It was a magnet there. Well, a piece of iron would have moved. Okay? So we don't know that this is a magnet, do we? Until we put the North Pole near this one, and guess what it's going to do? Attract it? No, it's going to move away. What would that mean? The North Pole of a magnet attracts the South Pole of another magnet. The North Pole of a magnet repels the North Pole of another magnet. Like poles repel each other, unlike poles attract each other. Okay, have you heard that before? Okay. Same thing went with charges. Like charges repel each other, unlike charges attract each other. The difference here, you can have a positive mono charge, okay? You can't have a positive charge without any negative charges being around. You can't have a negative charge without any positive charges being around. You can't have a North Pole without having a South Pole too. It automatically has to, without a doubt, have a South Pole. And if it has a South Pole, it has a North. So you can always test your magnets to see if they are magnets. If a known magnet attracts this and attracts this, this is not a magnet. It's just a piece of metal that's attracted to a magnet. But if it attracts this one and repels this one's got to be a magnet. Okay? If you know this one is. All right. A compass is simply a small magnetic needle that's free to rotate on a bearing. Now, what in the world is it that makes this magnet either attract that pole or repel this pole? Why? They aren't even touching each other. How can it attract? Well, there's a thing called a magnetic field. Same thing held true for electricity. Remember, this charge up here is going to act on this charge even though they may not be really close to each other because of the electric field. Magnets also have magnetic fields. A magnetic field is a field of force near a magnetic pole or near an electric current that can be detected using another magnet. Okay? Now, we're getting close to the next slide, but I don't think it's there yet, so let me test it and see. See. No. But I think we'll get to this real soon, so let's go on and hit it. Okay. Okay. All right. Before we get here, here's how we picture the magnetic field lines. I thought this would help, but it will a little bit. Okay? I'm going to make them red like they are in the book. In fact, they're already red. Let's just imagine that this isn't here. Okay? And that this isn't here. Okay? And that these two are actually the same magnet. Okay? Now, the field lines are represented by a line, that's why they call it a field line, that goes from this pole around to that pole. And we say they're moving in that direction. Okay? That's the field line. And you can almost see that here. See, these are going like this, and these are coming in like this. Now, this one over here is getting in the way, and this one's getting in the way. But that's basically what's going on. And you see in your book, you see probably a better picture of this. There's tons of them. I mean, for every little line of things here, there's a field line here, you know. And then there's some that you go off screen. There's plenty that go like this. Now, one thing, they don't cross. That one that I just drew looked like it crossed. Okay. So those are your field lines. Tons of them. And we always say, the convention is, they go from the north-seeking pole to the south-seeking pole. That's the direction of the field lines. Okay? In other words, if you were to take a little compass, okay, north is somewhere like that, isn't it? Y'all have any idea? Any idea? Super big. I think that's north that way. Okay? So if I were to take my little compass here, it's pointing, say, in this direction. If I were to bring it up here, then suddenly it starts pointing in that direction. If I brought it over here, it starts pointing in this direction. In other words, the field lines point in the same direction a small compass would point. So they point away from the north-seeking pole toward the south-seeking pole. Always in that manner. Okay? That's what the field lines are. The field lines are there, whether there's any iron filings, whether there's another magnet nearby, they're always there. Just like they are with electric field lines. Okay? There's two really good figures, figure 18.5A and B are excellent figures for this. This, however, is the figure for 18.6. Okay? Now this shows why north poles repel, or like poles repel, and unlike poles attract. Okay? Let's start with the attraction here. Because the field lines are leaving the north, moving toward the south, you bring another south here, all the iron filings crowd up in here because the field lines are like that. Because that's going to the closest south pole. There it is. And you got some that do like this and some that do like this. And that's what pulls them together. The field lines are trying to pull those two together, attract them. However, these field lines, remember, they leave the north and go out. Well, they're bumping into each other. And here's the thing. Field lines never, ever cross. Okay? These bunch up in there, but they don't cross each other. These, now you have to make them come here. You bring them together. Those field lines do not want to cross. They will not cross. So they're pushing away from each other because they're coming out here and just pushing away as hard as they can, above and below, and that's what forces them apart. It's sort of like a big spring there that's pushing apart. This is like a big spring yanking it together, okay? That's what the field lines are, and that's what they do. Okay? Does that make sense? That's why like poles repel each other and unlike poles attract. Now, they also have a figure 18.7, which they don't have in the slide set, that shows that field lines are actually three-dimensional. They're not just flat, planar. They're three-dimensional. There's, for every one you see there, there's one coming out of the board, into the board. They're just all over the place. Now, in your text, they bring up another definition here. I guess I'll do it here. I don't think we're going to do enough with this that you really need to worry about it. If I find out I'm wrong, I'll let you know. Magnetic flux. Okay. Let me get my dark pen back. We see field lines. They're just objects out there. By the way, fields are always related to forces. The stronger the field lines, the stronger the force. The stronger the force, the stronger the field lines, okay? Flux is also related, and magnetic flux, okay, is the total number of magnetic lines field lines, they just say lines of force, I'll say field, okay, lines of force, okay, entering or leaving the pole of a magnet. Again, I don't think you'll need this anything that we do, okay? The symbol for magnetic flux in the Greek letter phi, phi sounds like flux, kind of, right? Okay? And one magnetic line of force is given the unit of Maxwell. And frankly, I don't think I've ever used it, okay? The more useful unit is 10 to the 8th Maxwell, and 10 to the 8th Maxwell, because one Maxwell is so incredibly, incredibly tiny. And 10 to the 8th, that's 100 million Maxwells make one Weber, WB. And again, I don't think you're going to need that either. And what a Weber is the number of field lines per unit area, because make sure I'm saying that total number of entering, okay, I think it's actually newtons per Weber, the force per area that's crossing some imaginary shell. Okay, so force per unit, force per meter squared, or something like that. Okay, now, why is it that compasses point to the north, and the other point points to the south. Why is that true?
The magnetic field is stronger in the north.
Okay, magnetic field what?
Stronger towards the north. Because they always have
Okay.
the lights and all that. Most of the
Northern light. You're absolutely right. You're tying them together. The aurora borealis is the northern lights. Actually mean cold lights, but that's exactly it. That's because of the Earth's magnetic field. The Earth itself has a relatively strong magnetic field, okay, which is somewhat bizarre. And that's what we're going to talk about next. Here is, goodness, it's hot in here, the representation here. The Earth acts like a little magnet, okay? Oh, a little magnet, pretty big magnet, okay? And the trouble is, the Earth's magnetic pole is not quite the same place as the Earth's true axis of rotation, which is the true North Pole. With the true North Pole being right there, the magnetic North Pole is over here in northern Canada, near some of the islands in this is Hudson Bay down here, so it's above Hudson Bay, very, very close to the North Magnetic Pole. Okay? Now, same thing on the south. The South's geographic pole, you can't see it on this one. South geographic pole is here. The South Magnetic Pole is not even on the continent of Antarctica. It's just out to sea a little bit. It's actually a little bit further from the South geographic pole than the North Magnetic Pole is to the North True Pole, geographic pole. These are pretty close. The south one's a little bit further away. Now, the geographic equator, the equidistance between the two poles, is right there. To the true north, okay, geographic north. The north magnetic equator would be equidistant from these two poles. And since they aren't exactly along an axis, it's a little bit weird, but it's not too bad. Now, it's interesting how they draw this. They draw this part of the Earth and then something on the inside, which is part of the reason we do have the Earth act like a magnet. Does anyone know what the core of the Earth is made of, mostly? Okay, yeah, it's molten. Okay, well, actually there's two parts to it, but the element is mostly iron. Now, if you remember before, there's only 3 naturally occurring magnetic materials. Remember what they were? Iron, nickel, and cobalt, exactly. And the Earth, the core of the Earth is mostly iron, with a good amount of nickel, okay? I don't think there's much cobalt in there, but there's not much else. Mostly iron and nickel. Now, the crust of the Earth, now of course the water is on the surface of the Earth, but even though that goes down more than a mile in some places, way more than a mile in some places, it's still a little speckle or something on the globe. Most of the globe is solid material, right? Underneath the oceans is solid rock, okay? So, most of the Earth's crust, of course, is solid, except for the puddles of the ocean in there, okay? Beneath the crust is an area called the mantle, which is also solid rock. And that's most of the area here is mantle, but then you hit there's actually an outer core and an inner core. The outer core is liquid. It's so hot, there's so much pressure, there's so much friction that it's molten, it's melted, okay? So the inner part is melted. Now the inner part, the inner core, is solid again. There's just so much pressure it forces it back into a solid. We don't need to know all that now. The important thing is the rock shell that's out here, the mantle, is spinning around, and of course the liquid on the inside doesn't have to spin as fast, does it? Okay, so it just sort of sits there and it gets drug along some because it's not a smooth shell. It's not a ball bearing in there, okay? It's rough and jagged and, because of different rocks and stuff. So it pulls it kind of like a spoon stirring something in there. So it's making it spin some, and what's happening is knocking off electrons from one part of from the inner part of the mantle into the liquid. So therefore you have moving charges. Well, guess what a moving charge does? Creates a magnetic field. We're going to see that a little bit later. That's why the Earth acts like a magnet. Because those moving charges, as the Earth is spinning, and spinning pretty quickly down there, that it creates moving charges, and they create the magnetic field. Now, we don't need to go into this, but the weirdest thing, one of the weirdest things about physics that I've never heard explained at all, and certainly not convincingly, is the Earth's magnetic field has flipped about 22 times in history that they have record of. And to me, that makes no sense whatsoever. Okay? Now, the other thing is there's some times when the Earth's magnetic field is strong, and so other times it's very weak, and other times it changes direction. So it seems like to me that the spinning of those charges in there, I may be going the wrong way, whichever way they spin, it must be that they track and do this. Because once they're spinning this way, there's no magnetic field. And if they continue doing like this and spin this way, then it reverses and puts the north down here and the south up there. Okay? Which is bizarre, but it has happened. Now, how do they know this? They have drilled down into the crust of the Earth, and where magma has come up and solidified, and that magma is mostly iron, and you can make a magnet by placing a magnetic material like iron in the presence of a strong magnetic field and let it solidify there. And then all the little poles on the magnet, on the iron, line up with the field. And if the field is going the other direction, then they line up this way. And they have done cores down and seen the magnets go this way, then they go that way. Then they go this way, then they go that way. 22 times they've already detected they've reversed. Why, we do not know. My guess is that the spinning whirlpool in there must be going through some type of a weird cycle. Okay? And all the time mankind has been on the planet, which is a very short, very, very short period of the Earth's history, North Pole has been north. Okay, T, right? Okay. Let me find you in the book. There you are. Okay. My day on my thing is as far from the name list, so I have to make sure I'm in the right block going across. Okay. Now there's a new technologies blurb here that's probably well worth a read. I'll let you figure out what you're going to do with it, but it's pretty interesting. So let's move on to 18.2. That was all. 18.1 was just blah, 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 words, definitions, that kind of stuff. No problems yet. Now, I've already hinted at this. A moving charge induces a magnetic field. Got it? Moving charges create magnetic fields. There was a Danish physicist, first to discover a connection between electricity and magnetism in 1820. His name was Hans Christian Ørsted. Okay? Hans Christian Ørsted. He discovered that when a current, what is a current? Moving charge. When a current passes through a conductor, it forms a magnetic field. Now, it's usually a pretty weak magnetic field, but it does form a magnetic field. Okay, let's see if we have a, yeah, here it is. Okay, so this was discovered by Hans Christian Ørsted. Okay, now, let's say we have our compass. Okay, and that compass looks like it could be pointing sort of to the north, but there's no current through here. How can I tell you there's no current through there? Through that circuit? The switch is up, and for a current to move, you have to have a complete circuit. You do not have a complete circuit there. You have a gap right there. No current's moving. Okay? But, and you have this connected, it looks like a 9-volt battery to me. That's a pretty hefty little battery. And when you close the switch, though, and the current flows, and they say from the positive to the negative, then that induces a magnetic field. Which way does that field point? We use what we call the right-hand rule. Point your thumb of your right hand in the direction that the current's moving, and then the fingers are going to show the direction of the field lines, magnetic field lines. So they're leaving this way, there's north, coming this way, going back that way. So that one's doing that way. Okay? Uh-oh. They flipped the leads here. They put this lead on the minus pole and that lead on the positive pole. And then look what happens. Now the positive current is leaving here, going through here, going in this direction. So point your thumb in that direction. And now the field lines are pointing that way, looping up around. Now if you brought that, let me go back here. If you brought that magnet and put it on top of the line right here, it's underneath the line, and it's pointing that way. If you brought it on top of that line, then it would flip and go the other way, because the field lines are going around the wire. Okay? Same thing here. Right now, with it underneath, the field lines are doing that. If you brought it to the top, the north would point in that direction. Oh! I gave it away. Because here they're going to do exactly what I said. Here they have the switch open. Now the compass is on top of the wire, positive coming out of this way, so the current is going in that direction, right-hand rule there, and now it's coming above, and sure enough, the north pole is this way, whereas underneath it was that way. North is that way, but it makes the magnetic field produced by the wire is actually stronger than the Earth's magnetic field at that point. And then, when you reverse the wires and have it going this way, but the compass is on top, sure enough, the field lines are pointing that way. So you see, the field lines are going around the wire according to the right-hand rule. Now, remember, you put your right thumb in the direction of the positive charge, even though you know positive charges aren't moving. Okay? That's the conventional current, is what we call it. All right. Now, following Hans Christian Ørsted and, well, actually not following him, Andre Ampere was actually 2 years older than Ørsted, but he didn't live nearly as long. Okay? He was born in France. 1775. What happened that year? 1775. Yeah, that's the Declaration of Independence. So he was born on the year we declared independence from Britain. So along about, so he must not, okay. I've often thought that Benjamin Franklin may have interacted with him. No way. He would have only been, what? He was 25 years old at the turn of the century. I don't know. He could have. He could have. Because his work became the basis of science for electrodynamics following Ørsted's discovery in 1820. So, yeah. No. Franklin would have been much earlier than that. Okay, so I don't think they could have interacted much. Okay, I would have always thought Benjamin Franklin may have run into him, but if he did, he was a young kid, or Ampere. But anyway, the field actually curves around a straight current-carrying wire And what you can do, let's see if they have a figure of that. Yes, here it is. If you were to put a pretty strong current going up the wire, now this is a positive current, so your right hand thumb would point upward, and you see the field lines would be concentric circles, okay? If you were to sprinkle iron filings there, then you would see they all line up and do these little concentric circles. Now the trouble is you have to put a pretty strong current through there, and a pretty strong current might get really hot quickly, so you don't want to burn your paper or something. But that's exactly what's happened. Here's the right-hand rule, concentric circles. Put your right thumb in the direction of the current, and the right-hand rule shows the direction of the field line. So they go around the wire, okay? Now, so Ampere's rule, named after Andre Ampere, hold the wire in your right hand with your right thumb extended in the direction of the current. Your fingers circle the wire in the direction of the, they say the flux lines. I far prefer saying the field lines, okay? Flux lines are fine, but generally we talk about field lines, okay? Now, the magnetic field, let's see if this next one's on here. That's Ampere's law. No, not yet. We're going to get there. So maybe let's go back to the other one, because I probably need to write some stuff down. Okay. All right. The magnetic field near a long current-producing wire measured in units of Teslas. Now, do you think that's named after the electric car? No. Okay, the electric car is more named after it. There was a guy named Nikola Tesla, I think maybe it was. Actually, I think he was from Serbia or Croatia. I don't remember which. Oh, here it is. Nikola Tesla, born in Croatia. Okay? Now, I don't know if it was actually called Croatia back then, but that's what it is. He immigrated to the U.S., brilliant, brilliant guy, and went to work for another very, very brilliant guy, who you know the name pretty well, Thomas Edison. As far as I know, Thomas Edison still holds more patents than anyone else in U.S. history. He was an inventor and a half, and many of these were major, major, major breakthroughs. Incredible. I want to say genius. I think he probably was. Okay? But I think he was an ornery old cuss, too, which I think sometimes brilliant people are as well. Okay? And he, I think, probably recognized some of Tesla's ability, and Tesla went to work for him, but Tesla didn't always agree with him. And Edison was convinced that alternating current was excessively dangerous and to be avoided at all costs, and that direct current was the way to go to expand electricity. Well, Tesla was of a different opinion. He thought alternating current is the way to go, and direct current had too many limitations. They fussed and they fought on this, and I think they also had other things they were not agreeing on. In fact, I think maybe Edison was using them, not sufficiently rewarding him for his expertise and that kind of stuff. But anyway, Tesla broke away and went to work for Edison's rival, and you know this name pretty well, though you probably didn't know who it was named after. I think it was George. They don't list it in here. George Westinghouse. Ever heard that name before? Yeah, yeah. I think we have have had a washing machine and maybe dryer too that were named Westinghouse. Okay. Now, so he Tesla invented an electric motor, and that became the basis for most of the alternating current machinery. He sold his patents to Westinghouse. Okay, 'cause one thing Tesla was not good at, he was not a good money manager. He was a scientist, and he couldn't care too much less about the money, and he didn't handle his money well. I think he died a pauper. He then produced the most important inventions involving high-frequency electricity, the Tesla coil, resonant air core transformer, alternating current system illuminated the Chicago World's Fair in 1893, led to the construction of the Niagara Falls hydroelectric generating plant in 1896. His later inventions included wireless transmission of electricity, radio-controlled craft. He also worked on pulsed radar, harnessing solar power, radio communication. Wow! This guy was good. He was very good. And yet, I think he died poor, okay? Even though he had invented so much. But anyway, jumped off of Ampere's law. Remember, Ampere's law said, or his rule. Here's Ampere's law. B, whoops, let me get my pen color back. Okay? B is electric field strength. Okay? Now, they don't put it bold, but this is actually a vector quantity, so I'm going to put that on. This is, I'm sorry, I said electric. Magnetic field. That's what B is. Magnetic field. Okay, that's what B is. And B is equal to this quantity called mu naught. That's a constant. Okay? It happens to be 4 pi times 10 to the minus 7th Tesla meters per ampere. Kind of a weird unit. Okay? Times I, and that lets you know I is in ampere, so that cancels out the A, divided by 2 pi times R. And R is how far you are from that the current carrying wire. So that's why the R is in meters, and it cancels out the meter, and that gives you B in Tesla. That measures magnetic field. Okay? R is the perpendicular distance from the center of the wire. Okay? And that Tesla was named after Nikola Tesla. All right? Now, we talked about B, a field. The flux density, we mentioned that before, that is B is equal to phi over A. Where phi is the flux, magnetic flux, A is the area, so B, magnetic flux density, which is what we call that, magnetic flux per unit area. Okay? All right. And by the way, I don't think you need these, but in case you do, 1 Tesla is the same as 1 watt per meter squared. No, I don't think they have the units right. I think that's supposed to be 1 Weber, not. Let me think. Yeah, good, thank you. All right. I'm pretty sure that's got to be Weber, because that's what you measure flux as. In other words, flux density is B, that's flux per unit area. That's, I'm pretty sure is Weber per meter squared. Okay, and this would be measured in Tesla. Okay, so I think they got that wrong. The watt sounds right, but I don't think it is correct. Okay, where do you see that? Oh, you Googled it? Okay, so that's not W, that's WB, Weber. Okay. So here's example 1. I think we probably need Goodness, it's hot in here, isn't it? Man. You're cold? Okay. All right. A power line carrying 400 amps. What's that a measure of? Yeah. What do you measure in amps? Huh? No, joules are energy. Amps are charge per unit length. No, unit time. So this is current. I, remember our good old friend I? 400 amps, a power line carrying 400 amps is 90 or 9.00 meters above a transit used by a surveying student. So it's 9.00 meters from the transit. Now that's your distance, which I think they're calling capital R. Okay? So here's a student down here surveying, doing whatever he's doing, okay? He has this electronic equipment here, and somewhere up here is a line carrying 400 amps of current. Now, the trouble is, this is inferring that it's, okay, number one, 400 amps is a huge amount of current. I don't think any wire carries 400 amps. So this is sort of a made-up problem. Now, what's more, it's sort of implied here, this is direct current, because that's the only one that induces a magnetic field, okay? 400 amps of direct current is enormous, okay? And by the way, this is your 9.00 meters. That's up in the air. Now, 9 meters, what's that? Remember, we've done this before. I'm about 2 meters tall, a little less than it. And then that's about another meter to the ceiling. So that would be 3 meters. So this 9 meters would be a 3-story building. This is a 2-story building. Add one more floor there. That would be, and that's about what a power line would be, right? Something up there, maybe a little. Yeah, that's about right. Okay? So it's 9 meters above it. Okay? Find the magnetic field formed by the power line above the transit. Okay? Well, what is a magnetic field? That's B. That's actually a vector quantity, so I'm going to put it there, though you don't need it now. And that is mu naught times your current divided by 2 pi? Yeah, 2 pi times the radius. And the mu naught is 4 pi times 10 to the minus 7. 4 pi times 10 to the minus 7 Tesla meter per amp. Okay, Tesla meter per amp. Yeah. Times your I, which is 400 amps. And, of course, this amp cancels that amp out. Okay. Divided by 2 pi times your radius. And the radius was 9.00 meters. Okay? Now, fortunately, the 2 goes into 4 twice. The pi's cancel out completely. And you got 2 times 400 would be 800. I'll write it down. 800 times 10 to the minus 7. And by the way, the meters cancel that meter, so it's Tesla over 9.00. We already canceled out the units. Now, if you got a calculator, you can plug it in just the way I said there. 800 EE or EXP to the minus 7 divided by 9. Or you can move that decimal 2 places this way and make, because you made that number smaller, you make this larger, so that'd be 10 to the minus 5 because you reduced it by the other by 2, so 2 units. So any way you want to do it. See what your B will be, your field strength. Anyone got it yet? What's that?
I don't think I'm plugging it in right.
Okay.
Instead of 800.
Okay, no. Yeah, 800 EE or EXP negative 7 divided by 9. It's going to be a small number. Yeah, 9. Because the 0.00, you don't need to put it in the calculator.
At 0.50. No. Just 50.
Oh, 0, 0, 0, 0, 0. That sounds right. Okay. 8, 8, 8, 9. Okay, since we only have 3 digits anywhere, this will be, I'm going to write it in scientific notation, 8.89 times 10 to the 1, 2, 3, 4, 5, 6 minus 6 Tesla. Now that sounds pretty small. And it is fairly small, okay? Because he's a long way from it, okay? There it is. Okay, I couldn't see the answer. 8.89 times 10 to the negative 6 Tesla. All right, there is a B part to this. If the Earth's horizontal component of the magnetic field is 5.20, so I'm going to put BE for magnetic field of Earth is 5.20 times 10 to the minus 5 Tesla. Okay. At that location, what error could be introduced in the angular measurement? Assume that the power line runs north-south. You know, they haven't given us anything to do with that. I don't know where they got their basic equation there, because we sure haven't hit it, have we? Nowhere close. So, what's that? Yeah, let's disregard B. It's worked out there for you. And y'all haven't had enough trig either, I don't think, to do the next part of it anyway. So don't sweat it, okay? This was the part you did need to know, okay? Now, let's get out of this. Go back to, I'm sorry I've got the yawnsies. Seems like I've just been getting tighter and tighter all week long. And it's been nearly 2 weeks since I had a treatment, and I'm not bouncing back from this one very well at all. Okay, now, here's the deal. We have a wire here, and it has a magnetic field line that goes around it like this. That's usually pretty weak. So what happens if we take that wire and bend it into a coil? Now every one of those coils has, and the current runs through the same direction, don't back up on itself, so this one's doing like this one's doing like this. So these add to each other. So the tighter the coil, the more wires in it, you're adding and adding and adding field. Okay? Now that's what we call a solenoid. Okay? Here is the magnetic field in the coil. Remember, Now the current is going in this direction, and it's real hard to see. I think it's going around like that, so the current is like this. So the north is coming out, the south is coming in. So this is acting like a very strong magnet. The more coils you have, the stronger and stronger the field is. The more current you put through it, the stronger and stronger the field is. This is what we call a solenoid. And here's the iron filings. You can see the picture here. Here's the actual iron filings of this, and look how they concentrate in there. And then they begin to spread here, but they're strongest right there at the ends. Just like a bar magnet would do, right? Now, they're going to do something else here. They're going to do a coil of wire like this. Okay, let it hang there. I guess it's not real clear what that is. And then let's look at the little magnets. I mean, little compasses they put around here. And I hope that picture's better in the book, because I can't make much out of it here. Let's see what it looks like in the book. It's still pretty weak, okay? Yeah, okay. Here is the North Pole pointing this way, and then it's here, and then it's here, I think, and then it's here, and then it's here, and then it's, yeah. So, yeah, you can tell that the field lines are changing as you go around the coil. Okay. I think that's courtesy of something or another. I thought that maybe made sense, but it doesn't. Okay. So the iron filings show the magnetic lines of force from the magnetic field of a coil of red wire, who cares what color it is, charged with an electric current. The coil of the wire passes repeatedly through the white surface, that's the piece of paper that you got there, and the compasses also represent the magnetic field around the wire. And this is the coil of wire, and you can see the magnetic field lines are changing as you go around. Okay. All right. So the iron filings sort of show the strength of the field. The compasses show the direction of the field. Okay. Now, what we've just been describing there, I'm surprised they didn't say this. I've said it a couple times. A coil of tightly wrapped wire is called a solenoid. Okay? And just like we saw back here, that would be a solenoid with one north pole, one south pole. So here's your right-hand rule again. This time, you hold the solenoid in your hand and point your fingers in the direction that the wires are wrapped around, coming in. Hold it like this. Then your right thumb is going to point in the northern direction. So your right hand comes in really handy for a lot of stuff here. Okay, we call it the right-hand rule. Okay, which right-hand rules I don't like because I'm left-handed. No. Okay. The magnetic field around the straight wire is sort of weak, but around the loop, and I wish, let's see, do they show this? No, they don't. They show the figure in the book. A loop builds those. It enhances that, and then put many, many loops, you get a stronger and stronger wire. Stronger and stronger field. Now, for a long coil that is tightly turned, now, let's go back here. No, sorry. That was on the other side. Remember when I put B is equal to mu naught I blah, blah, blah. The magnetic field near a long current-carrying wire is measured this way. That's the magnetic field of a single wire with the current going up or down, either way. Okay? Now, if you have a coil of wires, then here's your formula. Okay. Here is the formula for this one. The field strength, let me get my pen back. Okay. The field strength here for a coil of wire is that same mu naught times that same I, but this time multiplied by N. What you reckon N is? Number of turns in that wire per unit length. So this would, let's just make a guess here, 1, 2, 3, 4, 5, 6. And that one up there, it looks like 6. This one here in the middle, maybe 5. That one over here, huge number, huge number. Okay? So you see your field strength, magnetic field, much, much stronger in a solenoid than it would be, a coil of wire, than it would be in a single wire. Okay? Because the mu naught I is the same, but now you're not dividing by some number that could be quite big. You're multiplying by a number that could be quite large. Sorry. All right, let's go back to our worksheet, I guess you would call it. Okay, here's example 2. Find the magnetic field. Okay, what's the symbol for magnetic field? B. So we're looking for B, and that usually is a vector. I usually like to put a vector symbol on it. Magnetic field at the center of a solenoid that is 0.25 meters long. So its length is 0.425 meters. I couldn't remember if I said the 4 or not. That's its length. And 0.0750 meters in diameter. So this is the diameter of that field of that solenoid, and has 3 layers of 850 turns each. So 3 times 850. Wow, and that's a significant number, digit. And that is what? 2550 turns. What symbol do we use for that? N, that's your N, how many turns, okay? And, it says when 0.250 amps flow throughout. So what's that a measure of? Current. That's your capital I. Okay? Now, the only thing that I do not see a purpose for here is the diameter, is it they called? Yeah. There's no place in here to use the diameter, okay, that I can see. Okay? Now, remember, I didn't quite say this right. This is not your N. I realized that shortly after I wrote it down. Your N is the number of turns per unit length. So we've got to calculate our N. Okay? So our N is number of turns, 2550 turns per unit length, and the length was 0.425 meters. So that's going to be turns per meter, which is going to be a really big number. Okay? So our B here is mu naught I times N, which is that 4 pi? I keep forgetting. Yeah, 4 pi times 10 to the minus 7 Tesla meters per amp, okay, times I, which is 0.250 amps, times 2550 turns, which is not a unit really, divided by 0.425 meters. That's how the length of it. Okay, notice this meter will cancel that one out, this amp will cancel that one out, and we're left with Tesla. So, do the math. That would be 4 pi EE or EXP negative 7 times 0.25 times 2550 divided by 0.425 equal. Know how you're doing. So 4 pi is going to be a little bit more than 12 times 10 to the minus 7 times 0.25, or a quarter of 12 is around 3 times 10 to the minus 7, and then multiply that by Okay, where are you talking about? Right here? That's 3 times 850. Well, we already did that. That was 2550, I think we got, right? And that's what you're putting up here. Yeah. Number of turns per unit length. Your length was 0.425 meters, so per unit length would be 1. So, you're going to get something, hopefully, I would say with an exponent of something on the order of 10 to the minus, that's a 2550. I can't even read my own writing, but that's what it is, 2550 divided by 0.425. I think you're going to get something generally on the order of 10 to the minus 4 or so.
So when I put it in, I got 0.00.
Okay, wait, let me write. 0.00 188 4956. Okay. 1.88 times 10 to the minus 3. And that's probably okay too, yeah. And that would be Tesla. Okay. Now let's see what we got there. 1.88 times 10 to the minus 3 Tesla. Hey, that's a lot more powerful than the last one we had, which was 10 to the minus 6 Tesla. This is 3 orders of magnitude more powerful. That's like 1,000 times more powerful. Okay, quite a bit stronger. All right. Everybody got it? Or any questions about it? Okay. That finishes 8.2. You can do any of the odd number exercises 1 through 13. All right. Now, you just see, I hate to get out of this, but I'd like to see what my next slide is. I don't remember looking at it. So I think I'm going to have to, sorry about this, hold on. You need this up any longer? Okay. Okay, let's see what the next slide is. Where in the world is that? I did see that.
I can see any more examples in this chapter.
That's, it says 1817,
It's on page 5.
512. There's 511.
So there's after 8.
Oh, there it is. I was looking on the wrong side of the page. Okay. So I think we've got a couple of definitions to do first. So let's go back to the other slide and go back to it, the current slide. All right. And I got to get my ink color back. Okay. Now, I think I've already used this terminology before, that a moving charge induces what? Moving charges in the Earth's core induces a magnetic field. And that's what happens in a wire. A moving charge in a wire, a current in a wire, induces a magnetic field. And you coil that wire up and you strengthen that field. Okay? So a moving charge induces a magnetic field. Okay? Now, induced magnetism is produced in a magnetic material such as iron when the magnetic material is placed in a magnetic field. Okay? Such as produced at the core of a current-carrying solenoid. Okay? Yeah. Okay? We've been talking about that. Now, here is a new term, an electromagnet. Basically, you take a solenoid, which is a coil of wire, and put an iron core in the middle of it. Now you've made what you call an electromagnet. An electromagnet consists of a solenoid and a magnetic core, and when a current passes through the solenoid, that sets up the magnetic field in that iron core, and you now have a magnet. Okay? And when the juice is turned on. When the juice is turned off, you don't have a magnet anymore. Okay? So this is called an electromagnet. It's a magnet when the electricity is on. It's not a magnet when the electricity is off. Okay? In magnetic materials, the atomic magnetic field lines line up with each other in regions called magnetic domains when no field is present. This is where the other slide comes in. Sorry about this. I didn't need that at all. I was going to write something on it, but it's just right there in your book. So here's what we want now from current slide. Now, yeah, okay. This is a average any old pickup piece of iron here. Now, believe it or not, every atom of iron in that piece of metal is a little magnet. A little magnet. A little magnet. There's quadrillions of them in any piece of iron. Okay? Now, here's the issue. Most of the time, those are randomly done. So there's no magnetic field. That's not a magnetic piece of material. Okay? So that's why they call it unmagnetized iron. But it contains in it tons and tons and tons of little magnets. Okay? Now, you take this and put it in a very weak field, like maybe the Earth's magnetic field, or maybe a little stronger than that, and now you get some of the ones sort of lining up, but some of them are still against that. So what you do is a slightly magnetized piece of iron that creates a very weak field. Put it in something strong, like a solenoid with a lot of current and a lot of turns, and suddenly you produced a very strong magnet. And guess what? These electromagnets like this, if you set aside a solenoid, is going to be many times stronger than the strongest permanent magnet you can make. Many times stronger. Okay? Now, do they all line up like this? No, this is sort of an idealized drawing. But each of these are called the magnetic domains. And they're random when the iron is not magnetized. They are weakly magnetized when they start to line up, and then they're strongly magnetized when they're in the presence of a very strong field. Now I'm going to give you a true story that happened to me. Okay? Remember me talking about our yard work when we bought the new house, right? It's an old house, but new to us. Well, before I started digging out the patio, we had discovered, because when we bought the house, they came in and surveyed to make sure exactly where our property line was. And one of the weird things was that our garage was here, the driveway here, the garage here, and then the property fence, the privacy fence, went from the back of the garage up to a corner post and then back across the alley. I mean, not across the alley, separating the alley. It was an old, miserable-looking fence, sort of falling apart. But between the garage and the fence was a shed, where I guess they stored their lawnmowers and stuff like this. It was in pathetic shape. Okay, it's on a hillside, dirt floor, leaky roof. It was just in lousy shape. And it was about to fall apart. Well, when they surveyed the property, I found out the garage, the shed, and the privacy fence was about 4 feet inside our property line. Our property line was out here on the other, beyond the garage. So the lady living next door, a really nice lady, but she was renting the house. And so I went to her and said, "Ma'am, are you aware that our property line is here?" I mean, she said, "No, I didn't know that. It doesn't matter to me." She didn't go out in the yard. She was pretty old. But she said, "Let me ask the landlady." And she called, talked with the landlady, who lived in Tuscaloosa. And she said, yeah, I know that. They just put it there to line up with the garage and the shed. Went back, but yeah, I know. And I said, "Well, does she have any objection? I'm going to replace this old rickety fence, tear down this old shed. Does she mind if I move the fence back to the property line so y'all don't have to mow our grass, over here?" And she said, "Oh, no. Perfectly fine." So I did that. So I was going to move that, and like I said, going up a hill. And so what I wanted to do was establish the corner, which I had here, and establish a new corner up there, and get it right on the stakes that they had from the surveying. Okay? I thought I had it pretty good. And our yard faces the backyard faces almost true north. Okay? Just happened to be. Our front of the house faces almost dead south, true south. So I had, it was hot and dry that summer. I told you all that story. And digging the post holes for the posts at the corners, and it was quite a way between them. That was hard going. But I'd have to dig a little bit, fill them with water, let it soak in, dig a little more, fill them with water, and that's how I dug the holes. Anyway, I got the post planted up here and the post planted there. So what my idea was to tie a string, drive a nail into it as high as I could this lower post. Okay, it wasn't that high, but as high as I could here, and run the string up to that one, tie it off there, and keep it really tight. Now the thing, it was up a hill, so it was near the bottom of this post and near the top of that post, but I got it off the ground so I could do that. And then I could set my other posts in. They needed to be 8 feet because the privacy fence that I was going to get was 8 feet length, so I needed them to connect to a post. So I needed to run those 8 feet, apart as they went up. So that's what I was doing. So this first nail up here was about as high as I could reach, and I was driving it into the post. I was doing this by myself, and the post was, a little wobbly because, it's planted down here, but this is far from it. It was a little wobbly. I'm a little wobbly, and I'm not a very good hammerer. My father used to say they were right-handed hammers and I was left-handed. But that, I don't think that was the issue. But that's what he said. And anyway, I was whamming away on it. It was a pretty tight old post, too. Hitting away on it, it was moving and stuff like this. And then the nail would, toom, and went flying out and went into the grass somewhere down here. So I bent down like this. I just had the hammer sort of loosely in my hand. And I was down here scratching around for the nail, and all of a sudden, it was on the end of the hammer. What? And then I realized what had happened. When I was banging away on that iron nail in almost true north direction, I was shaking up these little domains in the presence of the Earth's magnetic field lines, and I made that nail a little magnet. And my hammer had an iron head on it, and the nail was attracted to it. I probably wouldn't have found it except it stuck to my hammer. What's going on here? It really happened. True story. Anytime you perturb an iron or any other magnetic material in the presence of a field, you line up those domains. Okay? Now, that made a very weak permanent magnet. Do that in a very strong magnetic field, like a coil, and you have a very strong magnetic field, electromagnet. But the news on that is, as soon as you turn the juice off, they go right back to being random again. Because you force them into this alignment, and then you turn off the juice and they go random again. Maybe not quite as random as they were, but close to it. That's what we call an induced field. Okay? And they have you do some stuff with that, which is pretty good. And are we sadly out of time? The sadly part is what you're nodding at. Yeah, okay, I thought you were sad. Okay. We'll begin next time at 18:4. And this time I'll put my papers in the right place. Okay, if I can find my papers. There they are. Okay, 18:4. Yes, ma'am. Oh, okay, that's right.
I had emailed you, I didn't think I was going to make it.
Okay. Yeah, I think, well, I haven't looked at emails today, so if you did them today. Okay. Here's this one has one part, so it goes there. This one has two parts, so do A above the line, B below the line. All these are one parts. Now, number 7. What voltage is required to produce the current of 2.85 in the circuit below this circuit? 3 resistors in series. Okay? And they give you the current, so you don't use this voltage because that's what it's asking for. What is the voltage required to do that?
Okay.
And then this one has 3 parts. Put A above and B and C below. This one has 1 part, and this has 3. Put A above and B and C below. All right, good deal.
What was it again?
What's that?
What was the stuff you were just explaining?
Oh, okay, right. I'm sorry. I didn't realize you hadn't heard it either. This has 1 answer. Put it there. This has 2 answers, put A above the line, B below the line. These all have 1 answer, so put them on the line. When you get to 7, though, what voltage is required to produce a current of 2.85 amps in the circuit below? We'll use this circuit, 3 resistors in series. So don't use this. You're looking for the voltage, so don't use this voltage. They're giving you the current, and you use those 3 resistors. See how much voltage you need to do that. Now, in this problem, forget about that and use this voltage and find the current. Okay, so you're doing the reverse. And this one has 3 answers. You put A here, B and C down here. This has 1. This has 3, A here, B and C below. Okay, good deal. Thanks.
Oh, can you grade my test?
When did you turn it in? Huh? Is that it?
No.
Oh, yeah. Oh, will I grade it? Oh, I thought you said, have you graded it? I said, you just turned it in. No, okay. Yeah.
All right, so my question is, the wording on these problems, when I go back to the samples in the book,
right,
the wording is like totally different.
Okay.
So for the longest, I was confused because I was like, is this the same chapter? So see, like the first one, they ask you what's the magnitude of the charges.
Mm-hmm.
But then, like on the examples when we did it, we was doing it like this formula.
Yeah.
So I'm like, Okay, I'm confused
So
because
is it
it's
using that form?
yeah,
It's
because
K, Q.
Okay, Q is the magnitude of the charge.
okay.
Yeah.
So I'm like, this is confusing. So
Yeah.
it's like I did these down here because I knew what I was doing, but up
Right.
there I was like, I don't know.
Yeah,
Use
when
it
I
right.
pass this out, I say, my goodness, it's been a long time since we did that, you know, since we did the charge stuff. So yeah, that is a while back. But magnitude of the charge is the Q. What is the value for Q?
Okay. And like
Now, you see, when they say charge, it could be plus Q or minus Q. They're saying magnitude, forget about the sign. Just use the
because on
amount.
one of them, asked you, like number 2, it said, what's the direction of the electrostatic force?
Right.
So I'm
Okay.
like, okay, I did the what's the magnitude of the electrostatic force, but now it's asking you what is the direction. I'm like,
Right. Okay.
wait, did we go over direction? Am I
Yeah.
missing
Well,
something?
sort of we did. If you remember that let me go back to, that was at the early part of chapter 17. That's 16. Okay. All right.
We passed Coulomb's law.
Yeah.
And I got where the
Okay. Here's the force. Okay.
yeah, I did that one because that's how I got part 8. That
Right.
was the formula I used. But I'm like, now it's asking me what direction.
Okay. If you remember we always said, here's the field, okay?
Mm-hmm.
And the force on a test charge placed in the field, when they talk about the field, there it is. I knew it was here somewhere. The electric field is created in space beyond. So a positive charge, the field is always away from positive toward the negative. You see that?
Positive what?
Away from the positive charge toward the negative charge. Just like we said for magnetic fields, away from the North Pole toward the South Pole. The point always points in that direction.
Okay, so you said positive is away from the,
Yeah. So what is, okay.
and negative is to
Yeah.
the charge.
Yeah, it points away from the positive charge toward the negative charge.
Points away.
Okay. So what is the direction of the electrostatic force? I would say either toward or away from one of those charges. So you pick which one you want to refer to.
You said what was negative? Points toward?
Yeah.
Point.
On number 2,
If it was
Like-
a negative or a positive, you said
said
positive points away.
okay, yeah, the electric field points away from the positive charge toward the negative charge. So,
It's like I got the formula and I worked the part A part of it, but I'm like, no, which way?
Yeah.
Talking about direction, because I'm getting lost.
Yeah. yeah,
Okay.
that picture right there, I think will help you get that.
Okay.
What page is that?
On page 458, that little drawing up in the upper left corner. An electric field is created in the space around an object, and they don't even say it, but somewhere I know they say it. I'm trying to see where they say it.
Was it down at the bottom? I remember seeing it because I highlighted it.
Mm-hmm.
I'll look back over
Yeah.
that part. And I got one more question.
Okay.
I like on number 5, it asks
5. Okay.
find the length of a copper wire with a resistance of 0.0262 ohms per foot with a total resistance. So I did I didn't do, but the formula that I thought to use was the
Okay. This one may not be an obvious formula. Did I already erase that? I guess I did. Okay. Let me get it back. Okay. This, you almost just use your units. I don't know if you've noticed there. I use units a lot to help guide me through things. And I think that's a really pretty safe thing to do. So let's see what it says. Okay. It says here, which one is this, 5?
Mm-hmm.
Okay, what we're looking for, let me get my pen back. Okay. We're looking for the length of the, whatever it is, copper wire with a resistance of, and so this isn't quite resistance. This is what they call rho, resistance per unit length, which is 0.0262, okay, ohms per foot. Okay? Okay? So what we're looking for is a length, and that length, by the way, is going to be in feet, because this problem's in feet. Okay? And a total resistance, okay, so your R is going to be 1.75 ohms. Okay? Now, what do you need to multiply by this to cancel out feet and give you this?
So, the length?
The length. So you multiply rho times L, the ohms per foot, whatever that is in feet, that will give you R in ohms. So to solve for L, divide both sides by rho.
Divide by what? Hold on. Because that's what I did, but it's like, it's, I guess the number I got was humongous. So I was,
It is.
Okay, so I was doing it right. I
Mm-hmm.
was like, this number is way bigger than the number I even started out with.
Oh, yeah, yeah. Well, think about this. It's only got 2/100ths or almost 3/100ths of an ohm for every foot. And you got to get up to 1.75 ohms. So 2 feet would give you twice that. 3 feet would give you 3 times that. 4 feet would give you, now you're finally up to 1/10 of an ohm. Okay? So, yeah.
The way I was thinking is like, the formula was R is equal, no, it was PL, R is equal PL.
Yeah. Yeah, it's a rho, but yeah. Let me see where that one is. Yeah, rho L over A on page 464.
Yeah.
Okay. And your A doesn't change. So you can...
And I guess because I didn't have an A, that's why I was like, okay, I got to be using the right formula, but I don't know if the number's supposed to be.
The A is the same throughout, okay. So who cares about that?
Okay. So I basically I did it right when I was doing the division, but
right.
So I was like, multiplication would be too much, but I guess I wasn't sure when I did, so I was like, let me just find out. Okay. And I think, and we already talked about 7, but I was like, it ain't no circuit on here. So
now, I'm sorry I used rho. That's not the same rho as the one in the book. You thought it was, but it really isn't. This is a resistance per unit foot. I just used rho because I thought that's a good number. They actually use resistivity of rho, and that's ohm feet, not ohms per foot. Okay. But this is what we've got, and this is what you use in the problem. You happen, it happened to work out being the same, but that was just luck. I didn't know, I'd forgotten they use rho for resistivity, but they did. I should have remembered that.
All right, I think I got it now.
Got it? Does that make sense? Yeah. All right, good deal. Units are your friends. Be kind to them.